Magnesite is a mineral with the chemical formula magnesium carbonate. Mixed crystals of iron carbonate and magnesite possess a layered structure. Monolayers of carbonate groups alternate with magnesium monolayers as well as iron carbonate monolayers. Manganese, cobalt and nickel may also occur in small amounts. Occurrence. Magnesite occurs as veins in and an alteration product of ultramafic rocks, serpentinite and other magnesium-rich rock types in both contact and regional metamorphic terrains. These magnesites often are cryptocrystalline and contain silica in the form of opal or chert. Magnesite is also present within the regolith above ultramafic rocks as a secondary carbonate within soil and subsoil, where it is deposited as a consequence of dissolution of magnesium-bearing minerals by carbon dioxide within groundwaters. Formation. Magnesite can be formed via talc carbonate metasomatism of peridotite and other ultramafic rocks. Magnesite is formed via carbonation of olivine in the presence of water and carbon dioxide at elevated temperatures and high pressures typical of the green schist facies. Magnesite can also be formed via the carbonation of magnesium serpentine via the following reaction: 2 magnesium silicide O54 plus 3 CO2 magnesium silicide O102 plus 3 magnesium carbonate plus 3 H2O. However, when performing this reaction in the laboratory, the trihydrated form of magnesium carbonate will form at room temperature. This very observation led to the postulation of a dehydration barrier being involved in the low-temperature formation of anhydrous magnesium carbonate. Laboratory experiments with formamide, a liquid resembling water, have shown how no such dehydration barrier can be involved. The fundamental difficulty to nucleate anhydrous magnesium carbonate remains when using this non-aqueous solution. Not cation dehydration, but rather the spatial configuration of carbonate anions creates the barrier in the low-temperature nucleation of magnesite. Magnesite has been found in modern sediments, caves and soils. Its low-temperature formation is known to require alternations between precipitation and dissolution intervals. Magnesite was detected in meteorite ALH840001 and on planet Mars itself. Magnesite was identified on Mars using infrared spectroscopy from satellite orbit. Controversy still exists over the temperature of formation of this magnesite. Low-temperature formation has been suggested for the magnesite from the Mars-derived ALH840001 meteorite. The low-temperature formation of magnesite might well be of significance toward large-scale carbon sequestration. Magnesium-rich olivine favors production of magnesite from peridotite. Iron-rich olivine favors production of magnetite silica compositions. Magnesite can also be formed by way of metasomatism in skarn deposits in dolomitic limestones associated with wollastonite periclase and talc uses. Similar to the production of lime, magnesite can be burned in the presence of charcoal to produce magnesium oxide, which, in the form of a mineral, is known as periclase. Large quantities of magnesite are burned to make magnesium oxide, are an important refractory material used as a lining in blast furnaces, kilns and incinerators. Calcination temperatures determine the reactivity of resulting oxide products, and the classifications of light burnt and dead burnt refer to the surface area and resulting reactivity of the product, typically as determined by an industry metric of the iodine number. Light burnt product generally refers to calcination commencing at 450 degrees Celsius and proceeding to an upper limit of 900 degrees Celsius, which results in good surface area and reactivity. Above 900 degrees Celsius, the material loses its reactive crystalline structure and reverts to the chemically inert dead lead burnt product which is preferred for use in refractory materials such as furnace linings. Magnesite can also be used as a binder in flooring material. Furthermore, it is being used as a catalyst and filler in the production of synthetic rubber and in the preparation of magnesium chemicals and fertilizers. In fire assay, magnesite cupels can be used for cupellation, as the magnesite cupel will resist the high temperatures involved. Magnesite can be cut, drilled, and polished to form beads that are used in jewelry making. Magnesite beads can be dyed into a broad spectrum of bold colors, including a light blue color that mimics the appearance of turquoise. Occupational safety and health. People can be exposed to magnesite in the workplace by inhaling it, skin contact, and eye contact. United States. The Occupational Safety and Health Administration has set the legal limit for magnesite exposure in the workplace as 15 mg per cubic meter total exposure and 5 mg per cubic meter respiratory exposure over an 8-hour workday. The National Institute for Occupational Safety and Health has set a recommended exposure limit of 10 mg per cubic meter total exposure and 5 mg per cubic meter respiratory exposure over an 8-hour workday.